There's our last one. All right. Good morning, everybody. Welcome back to Algebra 2. Today, we deal with the final conic section. You ready for this? The hyperbola, right? The parabola we started with. And I wish I had, you know what, I'm gonna, before we go there, I'm just gonna just real quick sketch a little something, just to give us this overview of where we've been. Conic, excuse me, conic sections are slices of a cone, right? More specifically, of the true cone, which is not this. The true cone is what happens when you take a line with a slope and you spin it around a central axis. So you get a circle up here and you get a circle up here, right? The double cone. And when I slice it in various directions, I end up with different results, right? If we slice it perfectly flat, parallel to the base, you get a circle, right? It looks like an ellipse, my perspective drawing here, but you would get a circle slice. And if you then tilt that, we kind of looked at that on Friday, how tilting that gets you, right, an elongated circle slice out of it that is automatically an ellipse. And if we go instead parallel to the line, that face there, well, now what we have out of here is, if I connect that back point to this front point, up and over, I'm going to get, so around the edges of that cone, you end up with a parabola. And we know parabolas from quadratic equations, and they did all kinds of good stuff. But so far, each of our slices has hit only half of the double cone, or a one cone that we know from geometry. So what if instead we go even more vertical, right? And we go something like this. Now we get, not only do we have this piece here, but we also get that piece up there out of the double cone. And these things look almost like parabolas, but they're not. They're a little bit different. They're a little bit wonky. They are the hyperbolas. And while the graphs look kind of like parabolas, the equations actually remind us more of the ellipse. Okay? They do weird stuff. So let's get into more details there with, I'm actually going to go to the chapter, because I think the chapter actually starts us off with the best introduction. How are hyperbolas different than parabolas? What's the actual difference, other than the fact that you got two of them? Well, the fact that you have two of them is a critical component, because check this out. The hyperbola has the property that rays directed toward one focus are reflected toward the other focus. So remember our ellipse, right? An enclosed figure where between the focuses we could shine a ray any direction, it would bounce and hit the other focus. So from one focus hits the other focus. Or the parabola, right, takes any incoming parallel ray and directs it towards the one focus. That's all well and good. And if you wanted to create a solar cooker, solar death ray, you could do that because the sun's incoming rays are effectively parallel. You could focus them in one point. But what if you have lots of things coming at you from any direction towards you, but you'd rather reflect them away towards somebody else? The enemy. Enter hyperbolas. The hyperbolas are the best possible shape for creating a force field, okay? Okay, imagine, Star Wars force field, laser blast coming in. You set up a hyperbolic force field around yourself here. Okay, this is you. Hyperbolic force field. Enemy ships firing lasers at you, bouncing off, but not bouncing off in any random direction. We want it focused. We want to make sure incoming blaster bolts are redirected back to a targeted place that we can control. So if we could shift and control our hyperbolic shield, right? If it's movable, we can tilt it a little bit. We can direct where this point is and say, oh, incoming shot from this stormtrooper, bounce, boom, hit that stormtrooper, right? Very Jedi-like way. Instead of trying to line up your lightsaber at the exact right angle, bumper pool, gotta get it reflecting off the flat angle there. Forget that. Set up a hyperbolic shield and you don't have to worry about it, right? As long as you're at one focus, your enemy is at the other focus, every incoming shot, no matter where. You don't have to turn and rotate and change up everything. You just keep this pointed at him. How's that for pretty cool? And I will fully admit, I really didn't grasp that. I missed that part of hyperbolas until this text, actually. I didn't learn about that bit. For some reason, we always skip over hyperbolas as reflective surfaces. We see it with ellipses and parabolas, but they skip that for hyperbolas. But it's right here. That's super cool. So, how do we work with them then? There's the context. We've got the setup. How do we work with these? And pardon me for not setting up independent notes here. I'm just going to annotate and go through the textbook here. All points in a plane such that the absolute value of the differences of the distances from two fixed points is constant. Ooh, that's a mouthful. Absolute value of the differences. Okay, well, remember the ellipse. We took the distance from one focus to the curve to the other focus, and we added those distances together to get a constant. Instead, for the hyperbola, it's the difference of those distances. Focus to curve to focus. If you subtract those two numbers now, you will always get the same thing. All right, so again, it's all derived from distances and their relationships, but in this case, instead of one constant difference or constant sum of different distances, it's constant difference of distances. No, don't say that 5 times fast, you'll confuse yourself. Okay, so that's where it comes from. As far as the equation itself, here's an example. Look at it. Y squared, x squared. Again, you could go in either order here. Perfectly acceptable. Still equal to 1, just like the ellipse. Still y squared divided by something. Still x squared divided by something. Guess what? These are the same somethings that major and minor axes, but the difference is subtract. You take your ellipse equation and turn it from plus to minus. You will take that ellipse and you will flip it inside out. Take an ellipse, break it open like an egg, crack it open, turn it inside out so that it's facing the other ways, and now you've got a hyperbola. Not exactly, the actual shape of the curve is different, but visually here, I want you to see this, right? We take the opposite sign there, and now we've turned it inside out. Okay, this diagram, super important. This is how you graph them. This is how you create the graph of the hyperbola. Okay? You have a hidden center point, just like with the ellipse. There's a center point that we usually don't graph in, right? It's not part of the curve itself. Okay? And there's these distances. Here we've got A, and we've got B, right? Our major and minor axes, as it were. And those form a box. Always start with forming the box. You need your distances, your axes, distances form the size of your box. Can everyone see how I formed a box around those lengths? And I will walk through a full example start to finish here in a moment. Okay? Then what you do, this is the fun bit, right? We connect the diagonals of the box. Go all the way through, nice long diagonals through the corners of the box. Okay? Those will create your asymptotes. Okay? And the asymptotes are what sets the hyperbola apart from parabolas. Right? A parabolic curve goes off and extends forever and ever, right? Off to infinity. A hyperbola also extends off to infinity, but at some point way out there, it starts to flatline. Whereas the parabola, as you zoom in and zoom in and zoom in, you'll still have some curvature to it. A hyperbola, on the other hand, if you get way out there and you zoom in and zoom in, it starts to really look like a flat line, straight line, because it approaches that asymptote. It gets really, really close to being, but not quite exactly on that dashed line, that diagonal asymptote there. So if you zoom in here, you might mistake this for part of a parabola. But if you zoom out and you see enough of the curve, okay, you'll see these get pretty flat, and it looks more boomerang shaped, okay, than a nice bowl like the parabola does. That's the difference. That's the key. And drawing those asymptotes in makes it really easy to draw your hyperbola, because there's always a vertex on the end of your axes. So you have to go through that dot. Don't worry about where the focus is. This spot will not help you draw it in, just like the ellipse. It won't help you graph it. And then it's really easy to come in and be like, nope, nope, just like parabola. Or if you like, come in close to the diagonal, up, curve, hit the box, and curve away. Okay, a little bit of practice, and you can do that no problem. So graphing it is actually really simple. All you need is those distances. Okay? The computation to get the actual focal length then requires a little bit more effort. The center point, of course, this example here is on 0, 0. It shows up in the equation the exact same way. With centers at the origin. No, give me with centers not at the origin. Here we go. Right, super important box right here. Here's the equation. X minus h, y minus k, or y minus k, then x minus h. The order matters here now because it's subtracting. Which one you put first does make a difference because you'll always have one minus the other. Okay. So notice here I have x first, here I have y first. Here I have x over a, here I have y over a. Because the book is continuing with that standard of, they always call the first one a squared. Okay. And which one is it going to be? Notice the difference here, horizontal versus vertical. Direction of the transverse axis. Which one's the transverse axis? Is that A or B? Let's have a look. Transverse axis right here. Through the foci. It's the major one. It's through the foci. It's associated with A. Okay? There we go. So if you have this box in your notes, which you should, this is projection of transverse axis. Call it major axis if that helps you. Axis associated with A. Okay, whether that's horizontal or vertical. This tells you, right, is it a horizontal box or a vertical box? The other thing we need to do is figure out which side of the box it's opening on. Because, and I don't remember where they have the example in here. Not in standard form, no. They're all on the sides. Aha! Yep. Notice this one now, they're on the top and the bottom. Okay? Still the same process. One's top, one's on the bottom. So how do you figure that out? Which do they do? The transverse axis always connects the foci. Okay? So the transverse axis here is vertical. The equation is in the form y goes over the a. Okay. How do I know that one's the transverse axis? What if it's like a short, fat one, but it's on the top and the bottom? We'll get to that. Okay. Any questions at this point? Okay. Let's do this. I have here a different practice worksheet than the one you have. Just to do some examples. So here is my first hyperbola. I've got x squared over 20 minus y plus 1 squared over 10 equals 1. So notice I've got x first, x squared minus the y squared. Horizontal is dominating. This is what tells me which side of the box. I'm not comparing this to that. If the major minor helps you, go for it. But the reason they call it the transverse axis versus the conjugate axis is because they're no longer size dependent. Okay? The fact that this one is bigger doesn't mean anything. What is important is which one was in the lead. Okay? So back to the chapter there. Look at our, well, not for the origin, right? General one. Okay? So it's still a squared. So we still have to find the square root of that to get our actual distance. Okay? So, oh, no, not that guy. Worksheet, there we go. So we got to come in here, find what's the square root of 20, square root of 10. Okay? Square root of 20 would be, 20 is 4 times 5, so 2 root 5. And this would be 2 times 5. It's just still square root of 10. Let's get a decimal approximation. Close enough. Oh. Hang on, I gotta reset my calculator. Okay, 2 times square root of 5, 4.47. And square root of 10, 3.16. So we have a place for them on the number line. And we're going to go, this is associated with the x, so it's still moving horizontally. So horizontal to 4.47, almost, but not quite 4.5. So go out there to either side. Remember, because the x was centered on the origin. There's no minus up in here. The y, however, okay, we've got to shift our center point. Y plus 1, so it's actually down here is our center. So actually, let me move those points down. Okay, and how far are we going in the y direction? 3, and a little bit in the y direction. So 1, 2, 3, and a little bit more. Oh, come on, draw the dot in. There you go. And 1, 2, 3, and a little bit more up here. Okay. Don't draw in an ellipse. It's tempting now. You just want to create your dashed line box. Like so. I have my box. I have my 2 points. Now I can see where the diagonals, right, those corners of the box is. Draw your diagonals in. Like that, and just to make it easy on myself. There we go. Diagonals in. I've got a box. I've got my asymptotes. Questions on how we got that much? All based on where's the center, found exactly like you do with the ellipse. What are the lengths of my axes, found exactly like the ellipse. It's just the drawing that's different so far. Okay. Now we got to figure out which side of the box do I actually draw on. Do I draw in here and here, or do I draw there and there? Which way is it opening? Okay, because it could be stretched horizontally or vertically either way, but which way is it opening horizontally or vertically? This is one of the major changes over from the process of doing the ellipse. The ellipse, you were just comparing, hey, which one's bigger versus smaller? Okay, that's what determined if it was a vertical or a horizontal ellipse. Vertical versus horizontal hyperbola is based on which one comes first. I have x minus y first. It's a horizontal hyperbola. The transverse axis, okay, not necessarily the longest one, but the most important, goes horizontally. The transverse axis connects my foci, right? So I know my foci need to be horizontal. This is my transverse axis. The foci are somewhere there, okay? They're not on the graph. So that tells me my pieces need to be here and here. If you draw in your box can be precise. Your diagonals should be precise. Your curves at this point, as far as I'm concerned, I'd give you full credit for that. That's fine. You can do a little bit better. We can, oops, go back to whole thing. Thank you. We can do a little bit better. Remember, we want to hug that asymptote at the edges, curve down to hit that, oops, I missed, to hit that point there, and come back out to hug the asymptote on the other side. Okay? A little bit of practice with this. Nice and easy. And I think these are almost easier to draw an accurate picture of than a parabola. I think most hand-drawn parabolas truly turn out to be hyperbolic curves most of the time, because it's easier. It's natural for you to turn into more of a straight line at the extremities, especially when it gets so stretched out there anyways. Okay. Questions so far? We just have one more thing to do. Identifying the vertices and the foci, right? I went backwards. I sketched first. We got to identify the vertices and the foci. Vertices we got, right? That's these guys. That's where does the graph touch the box? Right there. So we need, well, our actual x distance, we're going to need to use that number, right? So it's positive and negative 4.47, or 2 root 5, and down 1. Okay, so the vertices are at positive and negative 2 root 5, comma, negative 1. Okay? How about the foci? The foci are still going to be at y negative 1. They're still on that transverse axis here. Okay? And they're going to be somewhere there. I'm not sure. How do we find that distance? If only there was another relationship that connected A, B, and C. For the hyperbolas. Let's see if we can find that. Equations of the asymptotes. Don't worry about this. Don't worry about it. Look at your box. Okay, for the equation of the asymptote. You can figure that out from there. You can find that focal distance. Maybe this has it. Foci is at C, comma 0, but C wasn't in here. Okay, let's go back to the picture. Where is C? C is from center all the way out to the focus. Still doesn't give it to us. Where do they tell us? It's got to be somewhere. I guess it's just in the example here. I was really hoping it would be more explicit in the actual notes there, but based on that distance formula, there you have it, right? Equation relating A, B, and C for a hyperbola. It's Pythagorean theorem all over again. This time, good news, C is where we expect it to be. C is the long one. And I think you can tell that from looking at the hyperbola, right? If the focus is now outside the bounds between the foci, between the vertices, okay, I think compare this to the endpoints of my ellipse. It would have been had the foci inside. So now they're outside. They're longer distance. Okay? Let me get rid of those extra lines there. So we have one there, and one here, which I think I've drawn a little too far on mine because it's going to be the same as the diagonal distance, right? This is the same right triangle. If I slide this over here, I have a right triangle. A squared plus B squared equals C squared. So if I just draw a circle with that radius, I'm going to land more like there would be my foci. Okay, but we can calculate it. We just got to take these two guys, okay, Pythagorean theorem that. So let's go over here to the side. And we'll take 2 root 5 squared plus root 10 squared. And we get, well, this would be 2 squared is 4 times 5. Oh, yeah, right, we started as 20. So the square of the square root of 20, we're back to 20 plus 10, we get 30. So our C is the square root of 30. 30 is 6 times 5. 2 times 3 times 5. There's nothing we can pull out of there. Square root of 30. Okay? But if you want decimal approximation, square root of 30, about 5.47. So, yeah, a little bit more than 5. Maybe I went even a little too far, right? 5.5. Okay, so add that now to your center point. Remember, this is focal distance from the center point. All of this is 5.47. Didn't quite get the color coding correct. Apologize for that. So our focus is going to be at plus or minus square root Nope, what are you doing? The heck is that? Plus or minus 30, comma, -1. Okay. Questions there? Still confused. No? Not too bad? It really isn't. A lot of people think of this one as the worst one, but once you've got all the ellipse stuff down, this isn't actually that much different. And again, I think the graphing is almost easier because drawing boxes and diagonal lines is much simpler than trying to get this curve to look nice. And then you just whip this thing inside there. The bounds make it really nice and obvious when you have it correct or not. Okay, so then for today's work, you have somewhere, all right, a parabola intervention worksheet. So everything you need is right there on the sheet, along with an additional example. Remember horizontal versus vertical, okay? If x is first, it's horizontal. If y is first, it's vertical. And what do we mean by that? We mean a horizontal hyperbola is on the x-axis. Pretend the center is at the origin. Horizontal hyperbola, those vertices are on the x-axis. If x is first, it crosses the x-axis. If y is first, it crosses the y-axis. It's on the y-axis, assuming you haven't, like, shifted it, right? That's probably the most confusing part. So jot that down. Like, if you are printing this out, have the worksheet there, or copying this in your notes, put that right there. Draw these little symbols. Remind yourself, which goes first, what way does it look like? That's the ultimate step. And then you have, right, setting up the equation based on the parameters, and then a couple of graphing practices there. Okay? Last call for questions. No, you're either too scared to ask or really confident. Okay. Let's vote for confidence, okay? Have at it. You've got 13 more minutes to work. Go ahead and get started. I think that was all we had, right? Yeah, because we did the quizzes yesterday. So, yep, that's it. You're fine. Go for it. Let me know if you do run into any issues or have a question on anything.